Here we are. Welcome everyone to our talk by Gary Centers. And I've got Seb Hoof here with me as well, one of the organisers, to join in with the discussion. And Gary's going to tell us about the stochastic model for fuzzy dark matter used by the Casper collaboration. Take it away, Gary.
Thank you, Dottie. I appreciate being invited to this workshop. It's an honor. I'm enjoying the format, even in the midst, I guess, unfortunately we have to do this format because of COVID, but, I'm actually enjoying it quite a bit so far. So it's not such a bad thing for the conference, at least. Let me just share my screen so we can get started here. Oh, I think you need to make me a co-host. Oh, wait, no, never mind. I'm already there. Can you guys see? Okay. So this is way further ahead than I wanted to be. Okay. So yeah, as Dottie introduced me, my name is Gary Centers. I'm a PhD student under Dimitri Budker in University of Mainz, Germany. Today I'll be giving a talk on what I've titled Stochastic Fluctuations of Bosonic Dark Matter and Statistical Inference. But before I get into that, I'd like to, I wasn't sure if all the participants were, certain that dark matter is a thing, so I'm going to spend the next 15 minutes or so motivating. I'm just kidding. At a conference like this, we can luckily skip these slides. I just left them because I like the pictures. But yeah, so the Budker group, we do a lot of experimental constraints on dark matter via many different approaches. You can see a full list of our publications on the website, but I will emphasize a couple of approaches that we use to exclude dark matter here, just as a brief overview. One is the global network of optical magnetometers. One is the global network of optical magnetometers for exotic physics searches, GNOME. It doesn't really look for, at least yet, for the dark matter that we're going to mainly focus on today, but it looks for more topological effects, right? You've got a network of shielded magnetometers, and they search for correlations among the network via a Earth-sized object traveling through the Earth. So this is a variety of different dark matter models it looks for, and it's a cool experiment. So this theme of shielded magnetometers is sort of expertise of our group. So another experiment, this one's a little bit closer to my heart since it's the one I work on, is the cosmic axion spin precession experiment, Casper. The proposal was, I think, in 2014. And there's a recent overview from Derek Jackson Kimball. But yeah, basically it's the same idea. You have a shielded magnetometer with some sample that can couple to the unknown dark matter field, and you search for those signals. So there's one other, it's kind of a sub experiment of Casper. By the way, results are coming soon from Casper Wind Low Field, the main experiments that were originally proposed, wind and electric. These use two different couplings to axion-like particles. But yeah, I mean, progress is going strong with these experiments, and we hope some preliminary characterizations and exclusions are coming within the next year, potentially. But a little while ago, we decided to use another apparatus to exclude dark matter, and we call it Casper Zulf. It uses 0 to ultra low field nuclear magnetic resonance. Essentially, it's another magnetometer in a shield, but this sort of apparatus uses NMR in a very weird regime. People are used to NMR in high magnetic fields where the Zeeman effect dominates. However, this is in 0 to ultra low field magnetic fields, and the J couplings dominate the interactions and signals that you see. And so this searches for dark matter via modulations of these J coupling interactions in the polarized samples. So this exclusion plot on the left you see here is sort of a collection of experimental or laboratory constraints of, well, also the supernova ones on there, this particular one. To date, this is not available yet, but it will be once the paper that was posted in the archive last year is published. And this plot is really what I'm going to be talking about today. So this is, a really, really low mass regime relative to some other dark matter experiments, even ones that are searching for the same types of particles, axion-like particles or QCD axions, etc. But, as all the participants I'm sure are aware, there actually are a lot of motivations for dark matter in this regime, and it even can extend past 10 to the minus 22, as I'm sure some conference presenters have discussed, and I'm sure most of you know, if you start relaxing the contribution of that dark matter candidate to the total energy content. So yeah, let me go on. So there's a collection of references here. It's definitely not complete, but I just pointed to some nice references that can maybe get you started. So let me expand on the types of dark matter I was just talking about. So this paper I can summarize really quickly. The archive posting that we have, it's really just a simple point. It was kind of known in the literature, but not really emphasized, and was easily missed before. It was missed by many experiments to date. And what I'm talking about are stochastic amplitude fluctuations is this title here, but I meant to say stochastic fluctuations and revised constraints on linear couplings in general, because if you start talking about pseudoscalar couplings, there are more distributed parameters you have to worry about. But I'll get into that in a bit. The main point of the paper is that if you ignore these distributed parameters, of course, it's effectively like a different signal model. And this impacts your statistical inference on experimental data that you collect, whether it be a null measurement, you didn't see anything, or even in the event of a detection. So this sort of magnitude of this correction, so to speak, like if you had ignored the distributions versus accounted for them, shows that, what we show is that you should relax these existing constraints that did ignore these parameters by a factor of roughly 3 to 10. You'll notice that this is, if you've read the paper, you'll notice this is different language than was originally posted. And so that's what I'm gonna be talking about today, are some updates that we've included after some nice review responses from some reviewers. And it's been pretty enlightening for myself, definitely myself, and I hope some of the co-authors. And that's what I'm going to be focusing on, is that this magnitude of this correction factor can depend on experimental details, model assumptions, and choice of inference framework. So what do I mean by bosonic dark matter, virialized ultralight fields? So the distributions that I use for these corrections are known in the literature. So I'm not claiming anything novel. And we keep a very simple picture, very like an isotropic dark matter, a bunch of waves, you add them together, you can, approximate as classical fields. This is the picture that we assume. You get a characteristic coherence time due to the dispersion that's governed, and then you have velocity distribution governed by the standard Hale-Mallow, virialized velocity distribution, and you get, and anyway, so if you have these high occupation numbers, right, these ultralight particles that need to make up this large energy density that we see, you can sort of approximate it as a classical field. And this is sort of the go-to trick that experimentalists use. Like, okay, I don't understand all this crazy string theory models and simulations of fuzzy dark matter, but if you tell me, oh, all you're looking for is a oscillating effect on your sample. So this is, we're very good at looking for oscillatory signals, and this is our expertise really. So the signal, a very simple signal model you can put forth for scalar or pseudoscalar couplings is just a sinusoidal oscillation with some unknown amplitude and coupling. Let me just describe some of these constants. This is just gamma would be just any generic coupling from standard model field to the dark matter field. C would be some constant determined by the experimental apparatus. Phi naught would be the amplitude. I'll get more into that in a second. And F phi would be the Doppler shifted Compton frequency that you see up here, and some random phase. And so this random phase is the main crux of one of the main distributions that we use. So for pseudoscalar, there's a couple extra parameters introduced by the gradient of the field. That's you have an extra mass term in front, and then you have what we like to call the wind effect, is that your signal is now proportional to your relative galactic velocity with respect to your detector. So what's been done in the literature thus far is to assume that the amplitude of this field is fixed by our local observational knowledge of the dark matter energy density. However, this isn't exactly true if you think about this field as a collection of these randomly phased fields, right? This classical field is a collection of all these randomly phased fields. And what you should actually write down is that this phi naught is not some fixed constant, but a distribution of potential amplitudes. This distribution is very similar to anyone who's known anything about like chaotic light, but you can get to it very quickly if you just add a bunch of coherent waves with random phase. It's this random phase that gives you this Rayleigh distribution, and it's more commonly known in the literature as written down as the energy density distribution, which would be an exponential, right? Just the square of this. A Rayleigh would be an exponential distribution, and that's what's more commonly in the literature. So it's known in literature this distribution is there. It's just been neglected, and it's sort of reasonable to neglect it in a regime where your measurement apparatus is much longer than the coherence time. Then you're sampling this distribution several times, and so it shouldn't matter too much if you had assumed some like RMS value, so to speak. However, what we're talking about today, like I said, are these really ultralight dark matter candidates, and the coherence time starts getting basically definitely longer than the experimental lifetimes, typical experimental lifetimes. And this is when you start realizing that you're only sampling this distribution once, or any of these distributed parameters, velocity or random phase, if that matters. That doesn't matter in some regimes. It ends up being a little more sensitive, right? You can get unlucky, right? So let's say you measured 1 year, you didn't see anything, you measure the next year, you see something, and nothing may have changed in your apparatus, right? It's just that this distribution picked a different value. And so now just this deterministic model is what we call this not ignorance, but the ignoring of these distributed parameters, and the stochastic model we say accounts for it. And so, like I said, for the pseudoscalar case, you have velocity and phase for when that matters. And we call these nuisance parameters. These are parameters that you don't know what they were during your measurement, and so you have to account for them in some way. But what we want to do is compare what people previously assumed to what we think people should have assumed under this simple dark matter picture. Also, Dottie said, feel free to interrupt if something's not clear. And anyway, so what I'm going to talk about is how to compare these two models and figure out how wrong we are when we neglect the stochastic behavior. So I'd like to just introduce like a generic, what I like to think of a generic way to set constraints based on some data that you've collected, right? So if you have a model for what you expect your signal to look like, or your signal plus background to look like, and what your background only model to look like, you can write down those two distributions, and I presume that the signal model has, let's say, a strength parameter, and you can sort of tune that strength parameter to shift that distribution around. And your job is to determine whether or not your observed data fits, one of those two distributions, either a distribution with some signal parameter, some value, or the background model with signal 0. So this is what they like to call a collection of simple hypotheses, or a composite of simple hypotheses. Composite hypothesis, right? So it's just this hypothesis space of different values of S, and it includes the background only distribution. And so your job is to determine what's, the biggest S I can say wasn't in my apparatus. So this is just a balancing of p-values, basically, of these two distributions. Right, you have this red line, which I like to call the detection threshold of your background only model. These would be like to, identify the signal, basically candidate events that you would investigate to see if they really are background or statistical fluctuations or not. And then you have the, your signal model, and you're trying to make sure that you're not having a false negative too often, because you want to make sure that you saw it. And so that's the idea. If you can just write down this distribution, it's very easy to get a limit, a threshold value. I call it just S here, which is that dark blue curve. And then you're excluding all stronger signals than that, because their type 2 error is much, much less. Your type 2 error is past this threshold of where you can guarantee that you didn't accidentally say it wasn't there. Anyway, so this is just a general overview of what I think is the simplest picture in terms of setting a limit, a one-sided limit. So let's go back to this simple case. I'll focus on just scalar dark matter for now, because it's only one nuisance parameter. Right, our job then is just to compare the two different signal models, right? This S plus B distribution under these two different assumptions, and then determine how this threshold changes based on those two different model assumptions. Okay, seems straightforward. All right, very good. All right, I came up with an answer, within the first week of thinking about this, and I was happy with it. And it was off. But nonetheless, we all started working on it, and a couple of the collaborators were fans of Bayesian approach, and we got drastically different results, and we were pretty surprised. As physicists, you expect there to be like one answer. I have an experimental apparatus with, some set noise floor, and there should be just some basically fixed approach to determine whether or not I did or did not see a certain signal model. To get a difference of a factor of, 5 between your choice of inference was a bit surprising. And it's not so surprising if you start digging in and you're familiar with Bayesian versus frequentist literature. And often what I think is a bit of a, what I now think is a bit of a cop-out is what they call Lindley's paradox, which is just this general disagreement between frequentist and Bayesian inference. There's some big philosophical differences between the two. And so people say, you're not answering the same question, exactly the same question. So it's not reasonable to, it's reasonable to expect that you get different results. So we went with that for a while, but we kind of resolved this paradox a little later, and I'll get into that. So let me just, to recap quickly on what am I talking about when I say Bayesian or frequentist. So I'm just going to review some basic probability, right? This is just conditional probabilities. If I had a deck of cards, this is 100% true. The probability of drawing ace of spades, given I had just drawn a different card, right? You can write down this conditional probability statement pretty quickly. However, so this is just Bayes' theorem. This has nothing to do with Bayesian inference yet. If you now switch this probability of A given B to the likelihood, right? So likelihood would be like some sampling distribution, like I was showing before with these distributions of the signal model plus background and just the background, right? These nested hypotheses. You can think of this as just some sampling distribution, and your goal is to determine so Bayes' theorem allows you to say, okay, I want to make, statements, probabilistic statements about the coupling strength, let's say. I just switched it directly to, the topic of our discussion today. Given my data, so normally you have your sampling distribution, which is like some fixed coupling strength. What's the likelihood to observe this data? And it's more of like there's debate about how people interpret the likelihood function, whether or not it's even a PDF. You can think of it as more like a fitting function. But really I like to think of it just like a sampling distribution. It's just a probability distribution, exactly like it's written here. Probability of getting this data value given some model parameters. But what a Bayes theorem allows you to do is like, no, I don't want to make a statement about whether or not, what's the likelihood of seeing a certain data. I want to make a statement about what's the probability of me seeing a specific coupling strength. So that's like kind of the beauty of Bayes theorem, is it allows us to make statistical statements about what we actually want to talk about. Whereas the likelihood is a little trickier to make statistical statements, and people often make mistakes. But once you apply Bayes theorem to a likelihood, you start getting disagreements. 1 second. Oh, sorry, Deutsche Bahn. Not Deutsche Bahn. The package. Forgot the DHL. Anyway, where was I? Okay, so Bayes theorem, you apply it to a likelihood, you get a posterior, what they call a posterior distribution for the coupling strength. However, what you require, and what's sort of the main departure from frequentist approach, is the requirement of this prior distribution on gamma. What is a prior distribution on gamma? It's your, what was often used as, it's your degree of belief on specific values of coupling strength without regarding your likelihood function. So Bayes' postulate is just assuming it's a uniform distribution. I don't know what it is. It could be any value. So I assume it's just a constant across this entire range of possible parameters. It's not exactly a probability distribution, but it's a reasonable assumption. So it seems. But there are, there's a whole bunch of literature on how to choose this prior and different types of priors and stuff. And I will touch on that today. But the main departure between frequentist and Bayesian inference, in my opinion, is just this statement. This is simple conditional probability, right? I mean, well, it is the definition of Bayesian inference as well. But it's just, do I stick with strictly my likelihood function and don't talk about any of the other quantities here? Or do I actually calculate a posterior so I can make statistical statements about the parameter of interest itself? So I hope that was sufficient. Sort of now the question is, we have what I call the nuisance parameter, right, which is this unknown amplitude of my signal, right? So I've got some fixed oscillation that could have been present, the fixed amplitude of some oscillation that could have been present in my apparatus. However, I don't know what amplitude it had. It was sampled from some known distribution, however. And so how to deal with that? Bayesian inference actually provides a very clear way forward in that regard to deal with a nuisance parameter. So I just include one more parameter besides the coupling strength in our model. That would be phi naught, this amplitude I talked about earlier. And there's just straightforward machinery in terms of how to account for this nuisance parameter. You just marginalize it out. For frequentist approaches regarding nuisance parameters, I mean, a nuisance parameter can also include some systematic that you've measured before, the distribution of, but let's say you weren't able to monitor it during your apparatus or something like this, you could account for it in the same way. But there are several frequentist approaches because of their, touchiness regarding looking at this likelihood as a PDF or not. And there's, there's a variety of different approaches to account for nuisance parameters. I won't really touch on most, except for just the marginalized likelihood today, or Monte Carlo if I get there. But for now, yeah, that's what I wanted to talk about. So I'm gonna wrap it up there. So I was gonna expand on the actual examples and doing the derivations, but I wasn't sure if this is too in depth for a talk. And if we want to, we can go a little bit more in depth. But really, the resolution to this factor of 3 versus factor of 10 that you saw was just this choice of prior. So uniform prior seems to be a very, like I said, natural choice of your degree of belief behind the coupling strength. However, there's some big problems with uniform prior in a number of cases. In particular, our example for this fixed oscillating signal, or this oscillating signal with some nuisance parameters, uniform prior actually blows up. Let's say it actually blows up your posterior if you do a change of variables. Let's say I was measuring the amplitude spectral density of this oscillation, right? So I took the Fourier transform, and then I took the Fourier transform, or let's say I look at the power spectral density of my potential signals, and I'm just evaluating whether or not this distribution of powers in each bin, whether or not they met which distribution or not. You would think that whether or not I'm using powers, or if I take the square root and I'm using amplitudes, like amplitude spectral densities, my constraints shouldn't really care if I took the square root of my test statistic that I was using there. And when you use a uniform prior for Bayesian case, you actually are unable to use a uniform prior when you switch to power. Let's say when compared to using just the complex components of the Fourier transform or amplitude. The Bayesian machinery using a uniform prior actually breaks down. And this was like a hint to us, like something's wrong. maybe we messed up. And if you dig through the literature, there's actually, and this is also in contrast to frequentist approaches, which don't care if you're using amplitude or power, et cetera. You get the same result the whole time. And so if you dig through the literature, you actually find out that there's this wealth of literature about objective priors. And this is a way to derive your prior distributions based on formal rules. So it actually does use the likelihood function, and it tries to sort of minimize the amount of information that you impact your posterior with, given the choice of prior. And it also makes it one of the main things that these objective priors do is they also satisfy this criteria of if you do a change of variables, your results don't change. Anyway, so that's more or less what I wanted to talk about today, just this resolution, this paradox. And if you, I'd like to thank everybody. I know it's a short talk, but I hope discussion can open up and we can go into a bit more detail. For the pseudoscalar case, I decided, in the paper that you guys will see, we just did some brute force approach where we just simulate everything, and you see that, like I said before, there's extra parameters, velocity and phase in some specific regimes. Like if you're looking for an upconverted, like you can, anyway, I can talk about phase if you guys are curious. But in any case, we just did a Monte Carlo, and you get a correction factor of up to 8.4 for a given type of pseudoscalar coupling, experiment searching for a pseudoscalar coupling. This factor of 8.4 can actually be reduced a bit, and usually is for experiments, because this is like the worst case scenario. The worst case scenario being you're aligning yourself to the average galactic velocity, relative velocity between your apparatus and the dark matter, right? This is just like your direction. We always say towards Cygnus, right? You have this main component of the velocity, but then you also have this random directionality chosen by the axion field itself. And this is of a similar magnitude to that net effect. And that impacts your inference because it could be anywhere. But depending on your alignment on Earth, you have a different projection basically to this average component. And so anyway, the main crux of the argument is that scalar dark matter who ignored scalar constraints, who ignored this, these distributions only need to be adjusted by a factor of roughly 3, whereas pseudoscalar needs to be adjusted by up to a factor of 8.4. But if Bayesian inference was used and a uniform prior was assumed, then this could also be up to a factor of roughly 10 and a little higher. So I'd like to, thank everybody. And if there's comments, or not everyone's included on this acknowledgement slide, it's still old. Also, I want to include references throughout, and I'll post the slides when I have all the references included. but yeah, that's my talk. I guess it was quite a bit shorter
No,
than.
that's brilliant. Thanks, Gary.
Okay.
Um, there's a lot of ways we can go. We can go with the questions here. I apologize. I was typing during the talk. I'm taking notes, so that
No
I
worries.
can so that I remember some questions and things for our discussion. Um, yeah, so I think kind of the first place I want to start in context of the workshop is a lot of talks in this workshop are about simulations of fuzzy dark matter, and
Yeah.
I'm going to kind of refer in the questions maybe to some of the talks already, but I know people are like maybe watching these talks out of sequence because of the format. So some things might only make sense when we come back at the end. But I haven't watched all the talks yet either. Anyway, a lot of the talks are about simulation,
Mm-hmm.
and um, we simulate this regime of fuzzy dark matter exactly on the coherence time. So the cosine part um, is integrated out.
Yeah, I
Um,
noticed that.
in
Unfortunately, when I was looking through the literature,
yes,
one of the reviewers was like, "Why don't you compare it to these simulations?" And I looked at like a few of them, and I was like, "Man, they're all averaging out sort of the effect. I mean, they're accounting for it, similar in the way that we do marginalization, but
well,
yeah,
so what happens in the modeling, in the simulation, and in cosmology is you can't follow that short time scale.
yeah,
So you don't know about the random phase in quite the same way, but the distribution for phi naught is what you're simulating actually. So I'm wondering if you know about the connection of that to simulation, if there is anything about this, whether this Rayleigh distribution is what we see in
Well, it agrees with the literature I'm familiar with. I mean, so if you're, like I said during the talk, if it's normally written in terms of this exponential distribution of energy density, right? Which is a result of these, which I believe agrees with the result of these simulations. Um, and
so do you know just which part of the literature in general you're thinking of
well, I
in
mean,
particular?
it's not regarding the simulation literature. I think
Mm,
we maybe have talked about this.
right.
Um, But let's say the Foster, if you're familiar with the Foster and Softy paper, I think of 2018, I think it
Yeah.
was. They do this, nice derivation of this using just, a collection of classical fields being summed over their velocity distribution, etc. And even in there, you see the Rayleigh distribution in that work because it's really just a sum of randomly phased fields that you get this Rayleigh distribution. And this is what in turn gives you the exponential distribution of energy density. It's really just this random phase. And so if
Yeah.
there's any model any simulation that does something other than a random phase, then it would disagree with this. I don't know how, because it depends on how they change that phase, but that would be a departure from this Rayleigh distribution.
Right, but then the phase isn't included, and we need to think about it. And hope, well, I hope that my question will prompt in the discussion that we talk about
Yeah,
a bit more when we've
yeah.
got the simulators on board. Um,
If I may add something to this, so
yeah, go ahead.
it looks like I mean the phase is important here for the signal, so it might actually be something that I don't know, to some extent. I mean, we should probably discuss this more, but maybe the simulations, as Dodi said, yeah, are probably not, maybe not sensitive to the phase like the experiment is, where where the signal strength directly depends on the phase. It also sounds like you could somehow, calculate like an effective amplitude by averaging, I mean, by kind of marginalizing out the effect of the phase on the signal.
So the phase here, we have to be careful because this phase here is sort of the end result of this sum of coherent, of coherent waves. Um, uh, right, this is like the end result, and it's actually not so important for the majority of the regimes that experimentalists are searching in because you're just counting so many periods of the oscillation. But in the case where there's a couple cases where experiments are up converting the DC component of this oscillation to, let's say, your detector's orient is rotating every day, so you have daily modulation among yearly modulation, etc. And if this frequency is much slower than, with respect to the length of, or yeah, the period of this oscillation is much slower than the length of the time of your measurement, then this starts mattering, right? This phase basically picks some random amplitude that's up converted to your modulated signal. But this is a very narrow regime so far that people can resolve the daily frequency with their apparatus, and two, talking about dark matter, I guess.
Yeah, maybe it would also be interesting, because I guess you can rephrase it, although you can calculate the size of the correction, in terms of the measurement time with respect to the coherence time, right? So you could say, if you have an experiment like this and that, then you would get a correction of that size, and so you can determine whether that's important or not. I don't know if this has been sort of written down somewhere, but I think it would be pretty useful for people to see if they're of the experiment that they think is sensitive to this.
I agree. That would be nice to actually have sort of this time time dependence where with respect to the coherence time where you cross over. We didn't do that. I mean, this crossover is pretty sharp.
So
we didn't really investigate it too much, but that would be interesting, because I mean, it's effectively, as you approach this coherence time, you're sampling this distribution maybe twice and then maybe 3 times, right? So there would be some nice it's probably not too hard to extend the results to this intermediate regime.
So, but in your paper, there is a model for the time dependence of phi naught, right? Because I remember this plot with this kind of block. Where does that time depend? I mean, so that's the coherence time is going into that, but where is it?
Are you talking about this figure?
Yeah, this guy.
Yeah, so this is the actual field value. This is updated figure because we wanted to go show more coherence times. This is like what we were talking about. It's just that at a rate roughly comparable to the coherence time, you're sampling this distribution, and it's just, I mean, this is derived actually by Andre Derivianco. He uses he derives a 2-point correlation function and utilizes that to simulate this field. This is the field value itself, phi of t.
Because this is the thing that we could directly compare, maybe during this workshop at some point. This is the thing we could directly compare to the results of a simulation. So, for example, the simulations by Siyu Xue or Philip March or Bodo or Lam, all have this. They simulate the amplitude of this on the coherence time. So we could see how well, obviously only statistically, this is described. We probably want to make some angle average in the halo. And actually, maybe when it comes to random phases, now I think about it, Dima Levkov's simulations begin with the assumption of random phase, and his analytical results, the simple form of them rely on it, but then statistically he says it doesn't actually matter. So in Dima's talk, he derived some results about condensation times for both stars, and I think similar results would apply to any kind of statistic that you're using. So he's got this this Landau kinetic equation, and what Lam asks him is what's the angle average here? What's not the angle average, the ensemble average? And for Dima, it's practically over the random phases in the simulation, but in practice, it doesn't matter what you're averaging over. I wonder that in the dark matter halo, we're not simulating the phase part of this field, the cosine MT bit, but that you get this effective ensemble average by angle averaging within the simulation. It's some kind of like ergodic.
Yeah, basically a principle of ergodicity.
Yeah. So this amplitude and this kind of behavior on the coherence time certainly it could be tested. So
yeah,
it'd be a very cool thing if someone could look at this during the workshop. I don't know whether we'll have time, but.
Yeah, I mean, from what I've seen in the literature, the distributions we use agree with what's there. In terms of particular simulations, I'm not sure because, like you said, they do this averaging, so to speak, on different, in different ways or in different places. They pick to, make their simulations easier in different ways. It seems, but yeah. I mean, yeah, it would be interesting to hear from the people who do simulations directly what they think of these distributions on sort of this small length scale.
Yeah. Seb, do you have another question? Because I have on this before we move on. I have a few more for other topics.
Okay. Then just continue. I have another question on the nuisance parameters, but we can just continue with your questions, I think.
Right. Well, two more things like immediately come to mind on this, and they relate to the other talks. One of them is in Lamb's talk, he talks a lot about vortices in the halo, in fuzzy dark matter halos.
I must imagine I didn't understand much of that and how it would impact me, but
so the vortices are places, and they're common places in the halo where there is complete interference. So the field here, once you make when you go to the non-relativistic limit and you switch to this cosine MT business and you add the Hermitian conjugate, the amplitude is actually a complex field and it interferes with itself. And that means that there are places where it can completely vanish, and they're these vortex lines that kind of wrap. So the coherence volume, you've got this coherence time. The coherence volume is like surrounded by places where the field's actually going completely to zero. And well, I'm kind of wondering in the model, in this model that gives the Rayleigh distribution, would it be accurately accounting for those?
The occurrence of those vortices.
For the fact that vortices might be passing through the experiment. So it's kind of relevant for GNOME. They're not. They're like short-lived topological defects.
Yeah.
Basically, and so in this distribution, we don't see any zeros cross.
No, not exactly zero, yeah, but it's possible for sure.
Yeah, right. So yeah, but if you've got a local experiment,
close to zero.
If you've got a local experiment like Casper, then yeah, maybe the chance that one of the zeros goes exactly through you is zero. But with something like GNOME,
well, if you're looking for the energy density distribution, it's exponential. Right? This is an exponential distribution.
Right.
So
there are zeros.
Yeah, so there's more zeros there. And I think that I don't know if that's where the origin of these vortices is. Is it really just the fact that you have this, exponential distribution of energy density across the galaxy, and that these zeros, basically the smooth transitions to a point where you have zero on accident? That's the definition of these vortices? Is that correct?
Well, so the fact that they're general, from what Lamb says, does come. Actually, no, it comes exactly from the assumption of random phases.
Yeah.
So yeah,
it must be this.
Yeah. If you start with this complex field, which is really the phase that you're saying, the field, this what you call the wave function, but it's not a wave function.
Yeah.
And if you take a field and you give it random phases, you will have zeros. But it's not the phase on this.
Not this one.
It's not the phase.
Yeah.
There, it's the phase in the velocity. So it's to do with the velocity structure. Anyway, I'll leave that question there for us. For people to pick up on in the discussion.
Yeah. I look forward to it.
Seb, you had another question about nuisance parameters.
Yeah, basically, I think you mentioned in the talk, but just to make sure. So what are the nuisance parameters that you consider? Because you talked about this in a very general way. But concretely, so what do you sort of marginalize over in terms of nuisance?
So in terms of the Bayesian approach, it's exactly as I wrote here, where you can just break out this joint prior as P of gamma times P of phi naught given gamma, but they're independent here. And then P of phi naught would be just this Rayleigh distribution that I talked about as a nuisance parameter. And that's the only one, like we just consider like the simplest case. Like I'm looking for, some oscillating signal given some set of some data with, I took some white noise for some set amount of time. And I'm looking for a coherent oscillation within that white noise. However, this coherent oscillation has a Rayleigh distributed amplitude. And so then you just include that distribution at the end as a nuisance parameter of the unknown amplitude.
Mm-hmm. Okay. No, I was just kind of because you talked about the differences when you use a uniform distribution and this sort of constructed prior, or this reference prior instead for gamma. So have you now? Okay, I wouldn't necessarily say that because I think Lindley's paradox is sort of the solution is sort of I think comes about by recognizing the differences between the two approaches. So basically, you've chosen, or you used a different prior, which is of course perfectly fine. But I was wondering if you've looked into sort of different priors. I mean, other than the uniform and this Berger prior.
So I was actually planning to go in a little bit more detail. The finer details, because it is actually a very our likelihood actually provides a very nice example for basically disagreements between Bayes and frequentist results.
No, it's definitely very nice. I mean, to have a real life example where this was realized and where this was worked out. I think it's a very nice example for future reference.
Yeah. So I have in the supplementary material that will be, we'll probably post the updated one to the archive soon, where we talk about this problem a little bit more in depth with regards to the uniform prior and its issues, and that people should be aware of when using. And in our particular case, it actually ends up being quickly a big problem. So this likelihood that you see here is the likelihood of seeing a data observed value, A, amplitude. It's just something like you can write it in terms of powers, and maybe it makes a little bit more sense, but it's just the power spectral density. You have some observed powers, and what's the likelihood of observing a power with respect to a expected signal power. But this is the amplitude, just the square root of this amplitude spectral density. So just for people who are listening, this P of AS is the prior that Seb and I are discussing. This is on the right is just the likelihood. And this is what Bayesian inference often quotes, is just that my posterior is proportional to my prior times my likelihood. This likelihood is very general. It's just the likelihood for searching for a oscillating signal in some data set over some given amount of time. And what we find, so let's see if I have it here with regards to a uniform prior. You get an answer, the machinery works and you get an answer very quickly with a uniform prior. However, let's say your experiment was actually measuring in powers instead, right? So you can just do a change of variables of your likelihood function and what's the likelihood of me observing a specific power given a specific signal strength. And if you try to do the same exact machinery with uniform prior when you're using this likelihood function in terms of power, you actually get a posterior that is non-normalizable. Basically, it's not a probability distribution function. And so that basically throws a big red flag. Right? The frequentist approach using both likelihoods, this one or the one you saw with the amplitudes up above, give the same exact result. If you just use this generic approach like I showed, with you just comparing p-values of the two distributions and finding this threshold, you get the same result regardless of if you're working in terms of powers or amplitudes of your Fourier, of your time domain signals. But the Bayesian result actually blows up and you don't even get an answer when you switch to power. And so this is sort of the hint that something's wrong. And I started diving into the literature to see what was going on. And this, the fact that some choices of priors give you sensitivity to even a change of variables of your distribution is one of the main problems with a uniform prior with a lot of different likelihoods. And so Jeffrey was one of the first people who came across this, I think, in the literature. What was it, in the 70s or something? And he started proposing ways to deal with this. And this is where you get Jeffrey's prior, and it's derived via formal rules, starting from formal rules from there. And it's been extended through the literature up until even very recently. And I'll send around, on my updated slides, I'll have a nice review of these objective priors and sort of this discussion of uniform priors and their problems. But back to your question, Seb, of did we try different priors? And actually, yes. Like my initial understanding before diving into literature was that Jeffrey's prior was just 1 over gamma, right? Like a logarithmic prior. This is often the case for a number of different distributions that it works out to be that. Even for some distributions, it ends up being a uniform prior. Jeffrey's prior is uniform for a Gaussian distribution, for example. But it's often quoted as 1 over gamma because I think for Poisson statistics, it is 1 over that, 1 over gamma, I think. Anyway, but it's very common than that, but actually it's derived via formal rules. And when you try just 1 over gamma for these likelihoods, it actually blows up immediately. You don't get fixed results. So you actually have to, yeah. Anyway, so you have to be very careful about your choice of prior with this particular likelihood.
Yeah, I mean, I guess my question was a bit motivated by, basically, of course, it's nice to have a prior with, kind of good properties, that doesn't show this behavior when you do a change of variables.
Yeah.
But well, I mean, these what you refer to as objective priors. I mean, at the end of the day, you have a given experiment, and that experiment can only measure, a certain quantity. All right. So of course, you can think about priors that would also work with a different type of experiment, but the kind of, I guess, direction that I was heading into is kind of trying to figure out if there is more information contained in that sort of, or if you have information available that you could use to construct a prior on gamma. Of course, these reference priors are fine, but at the end of the day, I think they're all to some extent still subjective choices, even though obviously they're constructed in a way that they have nice properties. But when it's kind of perhaps there is a discussion of that, but maybe you could once more say if you've sort of thought about any information that is contained in gamma in a physical or other information that you could use to construct a different prior, because at the end of the day you have an experiment and you can only measure one quantity. So I guess generally the aim should be, at least I think, in Bayesian statistics, to to construct the most reasonable prior that you can come up with.
Yeah.
And then of course
so,
see what the prior dependence is, but maybe you could just a few more minutes expound on that. That would be great.
Yeah. So I agree. You want to pick a prior, like you don't really want your prior, intuitively, you wouldn't want your prior to depend on the particular experiment that you're using, right? Like the traditional view of what a prior is like it's your degree of belief or the best guess on the distribution of possible gammas. And so like you said, yeah, what can I use to inform this distribution? And that could be previous experimental constraints, for example, like or theoretical cutoffs.
So can I just ask a minute, are we talking now about a nuisance parameter gamma or about the model parameter, the coupling?
So actually the coupling strength itself. So like I talked about in the talk, this Bayes' theorem requires a prior distribution for the coupling strength.
Yeah.
And that's what we're talking about. It's just like, it's what's required to use Bayesian machinery. You need something there. Assuming it's one is what's called uniform prior. What I'm talking about is objective priors, which are sometimes 1 over gamma.
No, I'm familiar with all that from cosmology. I was just wondering whether it is different for the case of a nuisance parameter that's being completely marginalized over versus a parameter that you care about, because you were kind of talking about whether or not you've got amplitude or power for something.
Yes,
but does it make more sense? But that's like a reference to what you're measuring, whereas a statement about the okay, so the amplitude of power.
Change
of variables, like change of variables in the likelihood, not change of variables in the prior.
Yeah. So okay. What I was talking about is, like let's say my data, that I'm working with just decided to be just to measure in a different variable, or do some transformation, some different transformation to the data.
Mm-hmm. Okay.
And relatively reasonable transformations of the data, you don't expect your results to change too much. So that's what I was talking about in terms of a change of variables.
Okay, that was change of variables in the data. I was thinking about change of variables in the prior.
Sorry.
So I was just a bit confused there. Carry on.
Yeah. I mean, there's a ton of jargon that comes with Bayesian inference, or really just statistical inference in general. So yeah, it's easy to get.
Oh, I always feel like there's a ton of jargon that comes with frequentist stuff. I don't even know what a p-value is. So
there's a lot of jargon.
I'm from a different background. Carry on. With Seb's question.
Yeah. So in terms of this prior, you want to pick a reasonable prior, and you don't really want it to depend on the particular experiment you're using traditionally. However, in the reference that I'll share on the slides, or I could just find right now, they talk about this sort of traditional viewpoint where like you want, but really what is the goal? The goal is that you want your prior to be as the least informative possible on your posterior, right? Like you want the data to speak for itself, and you don't want this, prior that you choose to strongly influence what the data is telling you. Like if you chose a delta function at some value, then obviously that would completely destroy any type of results you were trying to get based on your data. And so the goal is to pick a prior that's the least informative. What they mean is it has like the smallest influence on your posterior. So I mean, I was I struggled with this as well in the beginning. Like I don't know, like what does it mean to be like a reasonable uniform prior or not, like or a reasonable prior, and like a uniform seems to make a lot of sense. But then you start reading the literature with starting with Jeffries up until today, and there's a lot of problems, and you have to be really careful. I guess like a uniform prior ends up not being the least informative prior you can make, and it can actually have a drastic impact on your results. And that's shown very, very explicitly with the likelihood that we use in this paper. Like if I had just started in terms of measuring powers, I would have not been able to give you an answer using a uniform prior, or even a logarithmic prior, like 1 over gamma. And so the fact that it just breaks down immediately means that there needs to be a better approach to choosing this prior instead of just trying to pick it based on degree of belief, as they say. And
I mean,
I'm sure there's, Bayesian physicists who completely disagree with what I'm saying, but I don't know how they would I don't know how they would end up dealing with the problems that you run into with this particular likelihood.
yeah, I mean, I wouldn't call myself a hardcore Bayesian, but I think, I think a Bayesian would strongly disagree with, the prior containing the least information, because obviously, I mean, they want it to be informed by whatever their prior beliefs are and what kind of, and, uniform prior in that sense has also a problem, because, sort of natural values for uniform prior are, something between 0 and 1 and order 1. And so you're kind of effectively setting a scale for whatever you are putting the prior on. So it, will become very tricky to, or, it's sort of.
Well, and that's
putting,
why.
Yeah.
That's why you say, okay, let's approximate the Jeffreys prior as a log prior, because it doesn't choose a scale, but it's not normalized.
Yeah. But so okay. I guess these discussions can go on forever and never. So I think we should cut it short and perhaps continue this. But no, I mean, it's definitely a very good find, very nice illustration of in this paradox.
But if you try, I mean, like I said, like if you do try to use, like let's say 1 over gamma or even gamma equals 1, you can't even get Bayesian results with this likelihood. I mean, I don't know, maybe you can, but I don't know the way to do it. But if you just do it with like the very fundamental like Bayesian inference approaches, it breaks down. You don't get answers.
I guess it should depend on your support that you choose for, the kind of range you choose for gamma, because then you can normalize, I guess, any prior, right? If you have finite support, then you should be able to get results.
You have to.
If you allow for all values, like if you choose and you could an improper prior, then mathematically, of course, this will not work. But in practice, you have information on a sensible upper value of or a lower value of your quantities, right? So I think in practice it's a solvable problem. That's why I was kind of trying to go in this direction of seeing what kind of choices you can
choose like a sufficiently broad prior, for example, not just one, like something Gaussian or something, or you can choose cutoffs at
in the end, and all these things imply different prior beliefs, obviously, and it's I think generally good practice to compare these things. And as I said, I think someone who's very strongly leaning towards the Bayesian analysis side of things would not agree that you should try to objectify the priors, and would also of course disagree that there are objective priors to begin with, and they would embrace this as a benefit of Bayesian analysis. But I think this is that you can discuss these things for ages and ages.
So let me move us on to a couple more things. I want to carry on talking about priors for ages, but I'm going to ask about a couple, just two more things. So thinking about that again, maybe like the role of simulation, say, in changing, in possibly changing or informing these results. In dark matter searches, I think recently we've kind of learnt the importance of Milky Way substructure. So there are these papers about the Gaia sausage, and its effect on WIMP searches, and in general kind of tidal streams. Those things would also and could also drastically change this distribution for phi 0. If there was a stream, then there might be some peak of phi 0, also in the velocity distribution. So have you guys thought about that? If we then change if we change the model for the accretion history of the Milky Way, how much of an effect could that have? Would it be larger than your factor of 3 or smaller than your factor of 3?
So regarding the discussion of how the dark matter structure would change sort of this picture of a random phase amongst all the, individual constituents of the classical field, I'm not sure. But in terms of the velocity distribution in the streams and stuff like that, these are more, I don't know, more, let's say perturbative corrections to the velocity distribution than like drastic changes to it. And these would not change the discussion we had that I have included here too much. Like in the Foster Softy paper, I think they do this very nice, like the way from the very beginning, their approach is designed to include sort of changes to the velocity distribution. You have to account for streams and stuff like that. And so they do a very nice illustration of how that affects their limits. It, sort of lumps, energy density into different modes of this velocity distribution. But yeah, I mean, like for this paper and for everything we've done here, we've just assumed a very simple picture. I'm not sure how, more complicated structured dark matter would impact this this discussion.
Yeah, because it would be interesting if it impacted it in a very different way from fuzzy dark matter versus cold dark matter. So so the model in the Foster Safdie paper, they're in the regime where they're measuring for much longer than the coherence time most of the day.
They resolve the entire line width basically.
Right, so they're assuming that you're resolving the line width, and in that case as well, Kieran O'Hare's looked at the effect of streams and velocity distribution on the axion line width, but in the regime here, where you're talking about measuring, not for many, for smaller than an oscillation time, which is really the fuzzy dark matter regime, where the oscillation time is of order months, then the way that we model, streams, like we know that streams are different in fuzzy dark matter, and the streams are heated.
I'm not sure how. Yeah,
streams are exactly heated by the motion on periods of order the coherence time, and that could really change the way that we should be modeling substructure in an experimental signal in this fuzzy regime. So I think it would be something that would have to be informed by simulation, but
I mean, because
very interesting way to take your modeling here that's like really forced everyone to think about this, and I think it's very important. But it's somewhere where we need to go further, I think.
I think so too. I mean, it's very interesting to think about, like, I often do, but I'm not a simulator, someone who does simulations, but yeah, I mean, if you think about these streams, right, it's actually a sum of this isotropic dark matter like we're talking about here with this other contribution from this more structured, this more defined mode structure of these streams. And yeah, like asking this question of, okay, now I'm summing up all these random phases between these two different contributions. How does this change this distribution in the end for this energy density?
And the streams would be, if the streams are puffed by the quasi-particle heating of fuzzy dark matter, they'd have a very different distribution. We know that streams would have because of the reduction in subhalos. Streams would not be punctured in the same way. This can be used as a bound on fuzzy dark matter. So there's a lot of looking to detection. Like we know in the case, sorry, I'm repeating myself, from Foster Safdie, from Kieran O'Hare, about how we can O'Hare and Green, how we can learn about substructure of dark matter in the case where we measure the line width, where the axion mass, if it's an axion, or the scalar mass, if it's a scalar, is large. But where the scalar mass is small, where we're in fuzzy dark matter, what from the distribution phi naught, let's say we make a detection, we're not setting limits, from the distribution phi naught, what can we learn about substructure? And that's not something that's been thought about, but it comes up from your talk and in the context of the workshop. So
yeah,
hopefully we can talk about it more in the longer discussion session.
Yeah, one of the reviewer comments as well was like, we have observational evidence of dark matter energy density, our resolution of the dark matter energy density distribution in the galaxy, they said, was on the order of 10 parsecs. And this was super surprising to me. And actually there was so I went and looked at the reference, because what this would mean is that basically, since we don't see fluctuations at that length scale, that the stochastic and deterministic basically limits need to agree based on observational evidence of no fluctuation. But if you look at the paper that uses observational astronomical data, they got this 10 parsec resolution on dark matter energy density by doing galactic averages radially on the galactic length scale. So then like these fluctuations would be averaged out in that case. And then they were looking at radial, density fluctuations from there.
And yeah, and that's part of this averaging that we've just talked about as well. There's an averaging that goes on in the observations and also in the simulations. So
yeah. But I mean, it is interesting that maybe people could start trying to look for these, coherent, these fluctuations of energy density based on coherence length in astronomical observational data. I don't think it's been done yet. I don't know. Like this shows that on the order of 10 parsecs possible if you do these gigantic, averages. But what's possible if you don't do that? I'm not sure, and that could be interesting. For people to look at.
I think we should probably wrap up here. We've started a lot of questions that we'll hopefully pick up in the discussion. Seb, do you have any kind of final question?
No, I think that's all from my side. Thank you very much for the talk. So let's wrap up, and thanks Gary, thanks Seb. And we will carry on this discussion in the discussion session. I hope everyone's enjoyed it.
I look forward to it.
Okay. Right. Bye.